Hi, in the previous lesson, we learned about binary operations and how to make them with logic gates. So, in this video, we'll explore how computers perform these basic operations but created in Minecraft with redstone. I love personally doing them in Minecraft because it allows you to see how they work. We'll look at a binary counter, a half adder, a full adder, and a subtractor. First, let's see how binary counters can be recreated. Here it is. This is probably one of my first creations, and this is a binary counter. This binary counter counts numbers in base 2, so binary. When the lamp is turned off is 0, when the lamp is turned on is 1, and currently is still showing the number 4. So, when we press this button here, it counts, so it adds 1. But this is a synchronous counter. So there is a little bit of delay and it is like a ripple. And every time we add 1, the pattern changes just like a digital counter in a computer. But here I decided when I built this probably a year ago to make it to be able to reset itself. If we press this button, it powers all of them, and when we add 1, it just clears itself. How do we make it? So, the binary counter is just a bunch of copper balls stacked one after the other, and it turns like an inverted binary counter because when it's powered, it is not a 1, it is a 0. And when it's powered off, so let me click the button, it is powered off, so it is now 1 here. And we just read the input, and we add a NOT gate to invert the signal. And how do we reset it? So, when we have a signal coming from the bulb, which can be seen by the comparator, it powers this block, which powers the piston down below, which extends the the observer. And when the observer notices a change, if we add a current or a pulse, the observer will detect that. So here it is a 0, and the observer will detect that and send a short pulse to the observer, which will extend, and here it will power the bulb because there will be an update. Here it is probably better shown. This will be powered off, turning this on, and we just add 1. So let's see here. Let's add a 1, then another 1. Here, the observer was detected the change, powered this, turned off, and got back to its original place. Okay, so then I decided to do another one, but this one is a little bit different. This one is with a NOT gate at the front, so it doesn't make any change. So if I do this, it will again power off, and if I click this, all of them will reset. Okay, now let's look how to make a synchronous counter. Here I am at my first design of a synchronous counter. And as you can see, we send a short pulse and it updates at the same time. Here, these two updated at the same time and sent a change to this. This here was a prototype that worked not very good. It was a ripple counter, not a synchronous counter. Here you can see it, and it was actually slower and it used more resources, so it's not survival friendly. But as we can see, this counter is a bit clunky. It's big, large. So next I did multiple designs until I got to the perfect one for a synchronous counter. And here it updates and it takes less space. And now let's say what. So, in an asynchronous counter, as we saw already, each bit changes one after the other, like a ripple. This can cause more delays, which we don't like if we want to make our CPU as fast as possible. So, in a synchronous counter, all the bits update at the same time. So, let's look at it one more time. I don't think I clicked it. Here, it all updated at the same time. And now, also here I have a vertical, which this one, we also sent a short pulse and we power this, and the logic is the same as the other ones. If this one is powered on, the NOT gate is turned off, so there are no more pulses, and we stop the pulse being sent from here, so we stop the current. This stops for a tick, then this here, because it's turned off, when this powers off, this updates forward, and the swap stops the signal from going backwards and stopping the whole machine from working. Here it is the same logic. It uses more resources, yes. It takes more space, probably. Okay, now let's go to something more interesting. A half adder. Okay, so now we're here at my half adder. And our half adder adds 2 digits and takes out a sum and a carry out. So here we have an XOR gate for the answer for the sum and an AND gate for the carry out. So if let's turn them off both down. So if I power this, we'll have a sum 1. If I power the second one, we'll have a carry out 0, 1, and a sum 0, so 1, 0. Okay, so now this is my version of a full adder. I use a design for the XOR gate by I Love Indigo, and here we have a carry in, a sum, and a carry out. So this can be stacked one after the other. And here A is 1 plus 0 is 1 for the sum, and since we have nothing else, so let's say that we have a carry in 0, 1, and if everything is 1, so all of our inputs are 1, carry out 1, and sum 1. Okay, let's look at it at a bigger variant. So here is it stacked, and let's do a small calculation. So let's add 3 to 1, and we should have 4, so it's 0, 0, 1. And how does it work? We have an XOR gate, which takes them to another XOR gate. Then we have an XOR gate with the carry in. So if the sum is 0, this will be 0. If the sum is 1, this will be 1. If we have a carry in, it will be something like an inverted answer. So if we have 0 and this is 1, the sum will be 1. And if we have a sum 1 and a carry in 1, the sum will be 0 with a carry out, which is done by an OR gate from if we have an AND gate. So if these both are 1 or these both are with the 1 sum, we'll have a carry out. let's turn this off. And probably, as you've seen already, let's do something bigger. It is not synchronous. And probably that's because it uses a lot of material. Now, let's look on how to make a subtractor. So, I have made a subtractor by using gates, but it doesn't work like it should. Probably somewhere I have made a mistake and it's a mess. Easier is if you have already a working calculator for addition to use two's complement. And what do we do here? So, we have a switch if we want to be subtracting or adding. So, if it's on, we are subtracting. If it's off, we add, we make addition. So, right now, we make subtraction. And because we have an XOR gate, if I flick B, this is B input, this is A input, and I flick B, it will be 0, just if I put here a NOT gate. And if I flick it again, it will invert. Okay. But you may be asking yourself, if we add one carry in and we invert everything, we make 1, 1, 1, wouldn't it just appear like 4 ones? Or more if we stack it more? No, because we have 1 in the carry in addition, which will make 0, 0, 0, 0, and 1. So, why you may be asking yourself, why 1? Why there should be 1? There is no 1 there. And this is a hidden bit. A bit that isn't shown and it's not used. Let's summarize why this works. So, we invert all the bits, we add 1 in a carry in, and we add it to the final result. And there is just a hidden bit that we do not see and we do not use. We've seen how to make these builds. The counter, the half adder, and the full adder, and the subtractor, yes. And these are foundations of how computers work. Inside Minecraft, you can see each signal travel through the redstone and light up the outputs, which makes binary operations easy to visualize. That's why I use Minecraft to visualize how they work. And with just ones and zeros, or in this case on and offs with the redstone lamps, we can create the building blocks of an entire computer, which I'm currently in the process of thinking and creating. And if you enjoyed the video, please hit like, subscribe, share, and check the next video if it's already out. See ya. Bye.